This video is about refraction, one of the most exciting and important behaviors of light, both explaining why it happens, how it happens, obviously what it is, in the real world, and using the index of refraction equation to measure. Refraction explains why our eyeballs work. It explains why glasses work and mirrors, and lenses and so many things in our world. It involves light going from one medium to another. So when light passes from one medium to another, example, air to the lens of not really glass, but molecules that act like glass in my eye, or it could actually be glass, like a cup or a lens of glasses or water. The ray of light is bent, and it is bent as it enters the new medium, so it is bent specifically at the transition between one thing to another, between air and water, between glass and air, whatever it may be. The reason why it happens is that the speed of light changes due to the medium it's in. So this video, nope, guess not. This video, try to watch it on your own if you can, has a really good analogy of why this happens from 3:30 to 5:30. Really, it's thinking about like light as a marching band. And that marching band, right, has like the beginning of the band here and the end of the band here. And, oh, there we go. Let's see if we can watch it here. Just
that analogy I was talking about a second ago. And so imagine we have a marching band that's all walking together. And so we're looking at the marching band, the trumpet players, and we're looking at them from above. And as they're marching, they're trying to keep the space between them the same. So to the person to your left or the person to your right, we want to keep that exactly the same. And so imagine that they're marching down a road. You can see that they're going to keep that spacing between them the same. But let's say that there's a bunch of sand in the road. And so what's going to happen to their speed as they enter into the sand? Well, the ones that enter into the sand first are going to slow down. But since they kept that distance between them the same, you can see that the angle at which we came in equals the angle at which we came out. So we don't see that refraction going on. But now let's set it up so they're marching in at an angle like this. And so they're marching across, let's say, a parking lot, and they're going to hit some sand as well. So what happens is as they come in, which one is going to start to slow down first? Well, it's going to be this one right here. They're still going to keep this distance between all of them the same. And so watch what happens as they enter into the sand. You can see they're bending like that. And so we're going from a medium where it's faster to one where it's slower. So if I put in that normal right here, what happened? This is our angle of incidence, so it's big. What happens to our angle of refraction? It's going to be small. In other words, it's approaching that normal. And so you always, when you're looking at problems...
So he just used a lot of vocabulary that we haven't talked about yet, but we will. Another way you can think about this besides a marching band is a car. So imagine you're in a car and you're traveling on pavement so fast, and you're going to switch and travel into mud or gravel. But mud really works. Think about something really slow. It's going to really change your speed. Now, if you're just going straight, it's going to be like the image before this. All your wheels slow down. It doesn't matter that the first wheels slow down first before the second wheels, and eventually your car slows down. Now, if you imagine that you turn really fast, that's when you're going to skid, and that's when crazy things are going to happen, or you can do donuts on ice or whatever. That's what refraction is too. It's about a change in medium, change in surface, changing something's speed, and that something has kind of different parts changing its speed at different times. And that's why we get a bend. Now, the vocabulary he just used, you will use in your lab as well. Angle of incidence is talking about what's coming in. Let's go to our notes to take a look at this. So that is often written as angle of incidence. Okay, coming in. The angle that we see over here is the angle of refraction coming out. Both of those angles are measured from the normal. And the normal is just a perpendicular line that goes between the two surfaces. So it just goes straight through the air into the sand. Again, as you do this lab, you'll use this, do the lab 1, you'll use this language. So how do we measure and talk about refraction besides angles? All mediums have a measurement that is a constant that is known, called an index of refraction. It is how much a medium slows down light. So if we look at the examples, something that's not very dense like air doesn't really slow it down. Something that is very dense like diamond does slow it down a lot. And by slowing it down, it's going to refract it more, which is why diamonds are so shiny, because light is bending everywhere. Glass and water are kind of in between. And in general, the denser the material, the slower light travels. And the bigger the index of refraction, which is n. So we can say lowercase n is the index of refraction. Now, if we take a look at our formula that is in the box, we can think about what is what. Now, n is the index of refraction, which we know experimentally for many things, but many times we're calculating it too. V is the velocity of light, speed of light in the medium. And what are we comparing this to? Because you might have said air. Why isn't air just one, the same? Well, we're comparing it to the speed of light in a vacuum, which is c. That's that speed limit of the universe, which is 3 times 10 to the 8th. It's a constant, and it's always what it is. Light cannot go faster. So you should always get numbers for speeds of light in different mediums that are lower, like these that you can see. The bigger the n, the more different the velocity is between the constant number of c. So diamond with this bigger n has a slower velocity of light because it slows down more. We're just going to do one example here in your problem set. It's under the reflection and refraction section number 2. So pause the video if you need to get this out, but I'm going to keep going. These problems will only give you one number because they are assuming you know that c is a constant. C is always 3 times 10 to the 8th meters per second. So what is the speed of light? In diamond, that has an index of refraction of 2.42. So let's practice using the formula to see if we can match the number in your notes. So remember that index of refraction is n. Our formula is n equals c divided by v. Now we can rearrange this to write it to be less or more friendly. If we multiply v to both sides, all of a sudden we can say that c equals v times n. Now that is easier to understand. I would just kind of write that, or c equals v n in your notes because it's a little more friendly. All right, so back to using it. I'm running out of space. Hopefully you're not writing as big as me. So c is 3 times 10 to the 8th. V is velocity that we don't know, that we're trying to find. 2.42 is the n. We divide by 2.42. And you type that into your calculator, and you should get a very large number. That is the velocity of light in diamond meters per second. You have a lot of practice in Quest with this same formula. Just remember, C is always 3 times 10 to the 8th. If you're solving for a V, it should always be less than that.